time for an example. So here is a particular second-order linear homogeneous differential equation with constant coefficients. And the constant coefficients are 1, 10, and 21. And I chose this example because I know beforehand that it's going to end up in case 1 of the 3 cases. And I want to demonstrate case 1, which is the only one we've really discussed so far. So the goal is to write a general solution. So I will do that here, and general solution means we should be able to deal with any initial value problem that can possibly arise. So then I will discuss how it really does that. Okay, so general solution. So we make our guess, e to the lambda t. Plug in e to the lambda t. Then, for x prime prime, I get lambda squared e to the lambda t. For 10x prime, I get 10 lambda e to the lambda t. For 21x, I get 21 e to the lambda t equals 0. So for my guess to work, this has to hold. And I can divide by e to the lambda t everywhere that's not 0. So I can divide by it. And so I've got this polynomial, lambda squared plus 10. Sorry, I didn't mean to make that red. Lambda squared plus 10 lambda plus 21 equals 0. Great. So now I can just find the roots. So I'll factor this polynomial. But actually, no. I want to show you how to be lazy and encourage you to be lazy. Here's Mathematica, and solve this polynomial equals 0. Notice the 2 equal signs there for lambda. And there we are, -7 and -3. Cool. So we got x1 of t equals e to the -7t. So let me write down the solution. We got lambda equals -7 and -3. So lambda 1 is -7, lambda 2 is -3. You see we are in case 1, right? Case 1 was where we get 2 distinct real roots. These are real and distinct. So e to the -7t and x2. So these are both solutions. If you plug either of these into the differential equation, it will be satisfied. So here's our general solution then, according to all the theoretical stuff from before. C1 e to the -7t plus C2 e to the -3t. Great. Yeah, so let me just write that down. This is the general solution. Now, I want to show you something about how to type this in. So here I am in WebWork, which is where I took this problem from. And it asks, find the general solution, write C1 and C2 for your coefficients. And so I have used C1 and C2 for the coefficients. And so I'm just going to write this in. Okay, so here I go. Okay, so there I've typed it in, and I will check, and it looks like it is correct. But I want to show you something. If I type in 2 times C1, if I just multiply the first one by 2, then what does it say? It says incorrect. But actually, WebWork is wrong here, and I'm to blame, not WebWork, since I coded that problem. So if I multiply this by 2, I mean, this is still a solution. If I just chose x1 to be 2 times this, that would be a solution, and it's still linearly independent to this solution. So it's still true by all the general theory that this, with the 2 thrown in there, is still a general solution. So that should be marked correct, but it's not marked correct. So what I'm trying to tell you is, please write your general solution in standard form to be marked correct. So follow this kind of procedure, and don't multiply. Once you get your exponentials with base e, don't multiply by additional constants. Just write it as C1 times this bare exponential plus c2 times this bare exponential with no additional constants in front, even though technically you should be allowed to put those additional constants there. Okay, so the reason I am telling you this is because it's easier for me to tell you to write something in standard form than it is for me to code the problem so that it accounts for these other situations. It's basically just laziness on my part in writing the problem. Okay, what about initial values? So let's go back here and get rid of that 2. So far it's correct. So let's solve an initial value problem. So same differential equation, but now we're looking at x of 0 equals 1, x prime of 0 equals 0. All right, so if I want x of 0 to be 1 and x prime of 0 to be 0, so this is a particular set of initial conditions, then sorry, I think this was 1 here. This was supposed to be 1. Then, to impose those, you just plug in t equals 0 and just require those things. So for this one, for example, I would put in t equals 0. So x of 0 would be c1 times 1 plus c2 times 1. So this equation is c1 plus c2 equals 1. And this equation, well, to work out what is x prime of 0, I need to determine what is x prime first, right? So let me just quickly calculate that. X prime is negative 7c1 e to the negative 7t minus 3c2 e to the minus 3t. Okay, now plug in 0, and I get, so for this equation, on the left-hand side, I get negative 7c1 times 1 minus 3c2 times 1 equals 0. Okay, great. So now I have 2 equations and 2 unknowns, and I should be able to solve, right? Anytime you have 2 equations and 2 unknowns, you can solve. No, that's not true. Most of the time when you have 2 equations and 2 unknowns, you can solve. Here we can, because of the fact that these two functions are linearly independent. That's why we had all that stuff in the last video. It guarantees that this will always be solvable. So this will be solvable. Okay, so now I can do some algebra, maybe isolate, write c1 equals 1 minus c2, and then substitute that 1 minus c2 in for the c1 here. Then I'd have an equation involving only c2, and then I'd isolate c2, and it's so much boring algebra. So here is what I recommend. So I am using Mathematica because it's one tool that can do a lot of the things that are useful in courses like this. But you can use any tool that you are comfortable with. There are many tools for doing this sort of thing. So you can solve systems of equations. So for example, I can solve the system of equations c1 plus c2 equals 1 minus 7c1 minus 3c2 equals 0. Instead of having to do the algebra, I can just do this and tell it to solve. And there we are. C1 is negative 3/4 and C2 is 7/4. There's another way to do it. So let's hope we get the same answer if I do it this other way. So you can view these two equations as basically matrix applied to C1, C2 equals 1, a yellow 1, and a green 0, right? And the coefficients in this matrix would be 1 and 1, that's this equation, and then negative 7 and negative 3, that's the second equation. So then the vector c1 and c2 is the inverse of this matrix applied to this vector. So that's another way to do it. So let me just put this in view. So I can just define that matrix. Let's call it A. So you can just list the rows and columns like this. If you're used to MATLAB or you're using Python with NumPy or something like that, then you could use this method. Even if you don't have an algebra equation solver, you can use this method of just inverting a matrix. So there's A. If you want to see what it looks like, you can matrix form. So there, it looks like the correct thing, 1, 1, negative 7, negative 3. Okay, so let me get rid of that. And then what I want is the inverse of the matrix. So you can just look at what that is. It's that. But I don't care. I want to actually apply the inverse to the vector 1, 0, which is this vector on the right-hand side. And I get negative 3/4, 7/4, which is what I got before. Okay, so whatever method you want, including doing the algebra by hand, maybe just do that once. Do the algebra by hand once, and then become bored of doing that, and then go ahead and use the software, whatever software you want. So whatever method you use, you get C1 equals negative 3/4, and C2 equals 7/4. So the particular solution that we end up with is x of t equals negative 3/4 e to the minus 7t plus 7/4 e to the minus 3t. Cool. So the idea is that satisfies both the differential equation, it satisfies this, and it also satisfies that its value at 0 is 1 and the value of its derivative at 0 is 0. That's the idea. Okay, now let me go back to web work there and just do a quick check. So what was it again? Negative 3/4 and 7/4. Yay. Okay. So then you're asked to solve another initial value problem. And this one I will do more quickly. Or at least it'll look like I'm doing it more quickly with the power of pausing recordings. Okay, so here's our initial conditions. X of 0 equals 0, x prime of 0 equals 1. Plugging everything in, I got these two equations, which as a matrix looks like this, and I'm just trying to get a different output vector now. I'm trying to get the vector 0, 1 to come out rather than 1, 0. And so why don't I just go here and just put 0, 1 instead of 1, 0? Because it's the same matrix, basically. And I get negative 1/4, 1/4. Cool. So then that means that my particular solution to the original differential equation with these initial conditions is negative 1/4 times whatever x1 was, plus 1/4 times whatever x2 was, and let me go remember what those were, e to the negative 7t, e to the negative 3t. What is wrong with my handwriting here? And there's my solution. Okay, yay. Now, what I really want to do is show you how these two solutions can be used without that much more effort to solve a problem like another initial value problem with just some random choices of x of 0 and x prime of 0. So this one has x of 0 equals negative 2, x prime of 0 equals -2, but no matter what the choices are, sorry, no matter what the choices are, so let's say you want to solve, this is the differential equation, and then you want to solve the initial value problem, this, where x naught and v naught could be anything. Just in my particular setup, they happen to both be -2. Well, one thing you can do is do what was done here. Solve it with x naught being 1 and v naught being 0, and then solve it with x naught being 0 and v naught being 1. So that's what we did. So we found two possibilities. This one for the 1-0 situation and this one for the 0-1 situation. Let's give them different names. So let's call this one, I don't want to call it x sub 1 and x sub 2 because that would make you think more of these. How about, I don't know, y sub 1? No, let me think of a good notation. Yeah, you may have just noticed there some problems with my attempt to pause the recording. That's why the windows have been flying around. Okay, so I'm going to call this x superscript 0. How about that? Superscript 0 in parentheses. And then I'll call this one x superscript 1 in parentheses. Okay, just names for them. So we have found that x superscript 0 and x superscript 1 are both solutions to the differential equation, right? So when you apply L to them, you get 0. So that means any linear combination of them is also a solution, right? And we also have that this one at 0 is 1, and its derivative at 0 is 0. And this one, if you look at its value at 0 versus its derivative's value at 0, you get 0 and 1. So if you take, let's say so try this. Take x naught, this one, plus v naught, this one. Then, so let's call that x of t. Then x of 0 is x naught times 1 plus v naught times 0. So it's just x naught. And x prime of 0, well, x prime, so just computing x prime of t quickly, x prime of t is x naught this prime of t plus v naught this prime of t. So x prime of 0 is x naught times this evaluated at t equals 0, which is 0. So x naught times 0 plus v naught times 1. This is 1. So there. And look at that. This satisfies the initial conditions, right? It's a solution, first of all. It's a solution because it's a linear combination of solutions, right? These two are individually solutions. So linear combination is a solution, and it satisfies the initial conditions, right? These are the initial conditions, and we have them. So that's neat. When you find the particular solutions that satisfy the initial conditions 1, 0, and 0, 1, then that's a way of... then by taking very simple-looking linear combinations of them, you can easily satisfy any other initial conditions. This is basically just coming from linear algebra and the fact that to do this stuff, we found the inverse of a matrix. You don't have to do it this way. If you want to, you can solve this in the same way that you solve the other ones. But if you want to, this is just neat. So look what I can do to answer this question. I'm going to copy and paste these two into some slots. So I've got x naught and v naught, both are -2. So -2 times something plus -2 times something. So what I'm doing here is I'm filling in -2 times my answer to one of the blanks plus -2 times my answer to another blank. That should satisfy the initial conditions here. So in these parentheses, I will put copy and paste this thing. And in the second pair of parentheses, I will copy and paste this thing. And that should work. And it does. Of course, this is the answer I put in then, right? Of course, you can way simplify this, right? You can like distribute and combine terms. But who cares? Like WebWork can check the answer for you. You don't necessarily have to put in the cleanest looking answer.